Okay, well, let's get started. Thank you guys so much for attending. My name is Don Barnetson. I'm one of the co-chairs of the Interconnect project, and actually we have a new co-chair who's just joined us, Chris Kapuzinski, who's out there somewhere. There he is, somewhere in the great dark. And so thank you so much, Chris, for joining us. I'm also joined by Run from Drivenets. He's head of product, and we'll talk quite a bit about use cases here. So let's talk about what this Interconnect project is. And then we'll talk about what the use cases are around active electrical cables, which is really the focus of what we're trying to do. The specific proposal we have in front of us is around 112 gig per lane operation. I'll spend a little bit of time reviewing what that proposal looks like, and then a very strong call to action to please join us. We would love to have more participation so that we can get the best of everything in this community as we work towards ratification of this proposal and ultimately making it an official OCP spec. Let's start with what the Interconnect project is. Credo, my company, founded the Highwire Consortium in 1999. We ratified a specification for plug-and-play active electrical cables along with 46 other companies to really try to standardize everything that is not covered in the IEEE or the many MSAs that our industry lives in. And so this is around mechanical dimensions. If you go to the Experience Center or the Credo booth or perhaps other booths, you can see how important mechanics of these cables is really becoming as the networking density is increasing so high. Power consumption of the cables, bit error rates. Nobody really runs at the IEEE floor bit error rates, so trying to sort of bring a bar that we can all live with. And then a much more explicit CMIS register map to make it easier both for the device makers as well as the host makers to talk to this. The scope of what the Highwire Consortium took on was 56 gig per lanes. That spec was ratified in late 2021, and then the Highwire Consortium contributed that in its entirety to Open Compute and moved all of these activities over to create this new Interconnect project. The Interconnect project is dedicated to furthering the work that we began in the Highwire Consortium. Active electrical cables are copper cables that have clock and data recovery retimers in each end. And you might ask why we do this. Well, we do it for two reasons. So we're taking what is originally a single link with an analog connector, and we're breaking it into 3 links. The 2 links on the host side are standard IEEE AUI chip-to-module links, just like you would see for any type of an optics. And then the line side link between the 2 connectors is something that you can stabilize during a production test process, so it doesn't require any form of link training or auto negotiation or some of the more challenging parts of stabilizing an analog link. There's also many breakout and gearbox options that are possible in these cables, but the initial focus is just point-to-point and perhaps 2-to-1 breakout versions. The reason we're doing this is because DACs are becoming more challenging. So it wasn't that long ago when the whole data center was interconnected with copper, because copper used to go 100 meters. And then at the 10 gigabit generation, it went 10 meters. And at the 28 gig per lane generation, it went 5 meters. And at the same time, you can see from the cable volume ratio that that cable that's not traversing nearly as far is getting thicker and thicker and thicker. And it's getting to the point where it's not very usable at the kind of rack scale integrations that our customers are building. And so what we're starting to see is that fewer and fewer of the ports in a hyperscale data center are even plugged with passive copper cables. And perhaps at the 112 gigabit generation, none of them will be, or a very, very small number of them will be. So active electrical cables, because you have these retimers, allow us to run a much thinner conductor between the 2 ends, 75% less volume than a DAC. They offer significantly less power and cost than optics, about half the power and half the cost of optics. And they maintain the MTBF levels that we need in passive copper cables, closer to 100 million hours, rather than optics MTBF levels that are maybe optimistically 10 million hours, but actual mileage may vary, perhaps down to 1 million hours or less. Let's talk about use cases. There's 2 primary use cases we see for AECs in the industry. These distributed disaggregated chassis. We just had a great presentation on DDCs on the software side. And then NIC to TOR connections. So on the NIC to TOR side, the world was a passive copper place. As you can see in the orange bars, over the next 5 years, according to the 650 group, AECs will take up about 2/3 of the share. So we're going through a complete sea change from passive copper connecting NIC to TORs to primarily active electrical cables. And that's driven by 2 things. It's primarily driven by space. There's simply no space in these rack designs because they were defined 10 years ago, and now we're trying to put hundreds of terabits of connectivity in the rack, whereas they were really originally designed for tens of gigabits of connectivity. But we can also offer various functions, gearboxing, speed shifting, the switching functionality that we enabled with Microsoft last year, et cetera. But DDCs are perhaps even a more interesting piece of this. And with that, I'd like to introduce Run, who can talk about the DDC side.
Thank you, Don. Am I good on the audio? I think so. OK, so what is a DDC? Well, you saw it in the previous presentation from Golan, from Broadcom. DDC, distributed disaggregated chassis. You can see it in the picture here. Essentially what we did, we took a chassis, we broke it into its basic component, and we wrapped up or packaged every such component in a standalone device. Then we grouped the whole thing together. And the software is what makes it from a bunch of various devices into one unified device. Everything here is OCP standard devices. The DDC as a spec is something which was contributed by AT&T a few years back, and it's been evolving ever since. There's an ecosystem behind this. The use cases, as Don mentioned, being demonstrated out there in the Experience Center. We have a cluster, a DDC cluster, which is on display. Devices are coming from UFI space, even though the ecosystem is wider than this. So there are other ODMs which have their boxes into this, pushed into this game. Connectivity, again, in the demonstration shown, is coming from Credo, obviously. Any type of connectivity will work just as well. It's not that it's kind of confined to using just one specific vendor. That's the whole purpose of the ecosystem. And the software as well. It's currently running Drivenets software on top of the DDC, but there are other software versions that still run on that same infrastructure. Even the same devices can be run with a different cluster, with a different software. So there's really no limitation, and it's a real open ecosystem. A little bit about the size. One of the attributes of a DDC, a distributed chassis, is the fact that there is no chassis. So the chassis itself, the metal enclosure, is somewhat of a limitation when you build a high-scale system. In a way, it's limiting to the point that the full radix of the ASIC is not fulfilled when you build it into a chassis. All sorts of constraints, which we heard all day long and yesterday, power limitation, cooling limitation. All of this is kind of diminished when you break it up into multiple devices. And these multiple devices can spread not just within one enclosure, but within several racks in a data center. So in terms of heat dissipation, overall power consumption, there is a lot higher level of complexity or flexibility that you can endure into your implementation and still get to the highest scale in terms of the radix. We're contemplating in kind of future perspective about creating a multi-tiered of a DDC. So what you've seen in previous pictures, there is an NCP. By the way, NCP is a Drivenets terminology. It stands for Network Cloud Packet Forwarder. The original OCP termination is DCP. So it's disaggregated chassis packet forwarder, and then DCF on top. So we can create 2 tiers of DCF. So it's 2 layers of fabric, one on top of the other, which kind of breaks the fan out into something which is really explosive. We're talking about tens of thousands of interfaces. Yeah, in a way you can see it. Here now. The benefit that we have seen, and this is specifically here for the purpose of data center implementation, and again, this was mentioned in the previous session from Golan, there are benefits to running a cell-based fabric when you're implementing high-frequency, high-performance computing or AI, ML, such workloads. The distribution of traffic within this fabric of devices is completely leveled. And anything to do with mice, elephant flows, jumbo frames, or whatnot is kind of buried within how this architecture is being built. Has nothing to do with what we Drivenets have done. This is a classic attribute of the architecture coming from the silicon level. And then the implementation, in a way, the way that it kind of aligns to high wire or AECs, or how this is coming up into play. This is one type of topology that a DDC can be installed. Everything in gray is servers, and then you have the blue devices, which are the NCPs or DCPs, the packet forwarder, or the alignment of what you would have as a line card if this was an actual chassis. And then the green ones are the fabric elements. So one option is to put everything together in one single rack, and this is somewhat the example that we're showing in the Experience Center. Everything to do with the connectivity, when it's installed within one rack, is something that you can run on copper. Because of the distance, it's very trivial, it's very simple. Most of the deployments that we do have are in such formation. But when you take this into the data center, in many cases, it's preferred to have this type, or maybe it doesn't work. There you go. This type of a topology. The graphic is gratitude to Microsoft's PowerPoint. I didn't do anything. And then in this case, every NCP or DCP is in fact located as a top of rack. And then the internal connectivity, or actually the network connectivity from the servers, GPUs, to that top of rack is being done on copper. And then the internal connectivity between these spread top of rack devices and the fabric elements, which can be elsewhere in the data center, then this can be a longer reach. In this case, can be fiber, an AOC, or somewhat of a pluggable. That's it for the example on the Drivenet side. I'll bring it back to you.
Cool. Thanks so much, Ren. So let's get into the open proposal that we have in front of our Interconnect group today. So we're trying to standardize 112 gig per lane products. This would include a 1.6T OSFP XD, which you can see in the Experience Center in the Credo booth today, along with a number of 800 and 400 gig products in point-to-point as well as breakout configurations. If we dig into what the specs here, actually before I do that, we're very much open to other configurations, so this is not set in stone. So if there's a favorite configuration of cable, please come to us. We would love to have more input. As I dig into the specs, this is from a 400 gig QSFP 112 to QSFP 112 example. So what we're looking to do is to standardize the prefect bit error rate and power consumption and latency and those basic electrical functionality that are not built into the IEEE or the MSA specs. And then mechanically, there's no group beyond standardizing the connectors who's done really any work in this. And so we're looking to say, for a given length of cable, what is the maximum thickness of that cable, the maximum outside diameter? How does that need to bend? What's the bend space? What's the bend radius? What is the length tolerance? All of the things that are required in order to build DDCs at the kind of densities that Ron just showed in a way that you can substitute our products so that you can buy a cable from Credo, perhaps in the future from another vendor, and they will indeed be plug-and-play identical products. So with that, let me go to the call to action. Please join us. We have calls on, I believe, the third Tuesday of every month. You can find them on the OCP site. Please join our calls or join our mailing list. We would love to have your participation. We would love to have other eyes on what we're doing. And our goal is to move the 112 gig per lane spec towards ratification in the coming months so that we can have something and then start looking at what is going to be a much harder climb, the 224 next. With that, thank you so much for your time. And I think we maybe have one question.
Yeah,
but
maybe a
thank
question?
you. Cheers.